Welcome students. Now we are in the continuation of our lesson of 10th class physical science, reflection of light on curved surfaces. So far in the previous videos we just came to know about how the different spherical surfaces reflect light, and we came to know that there are two reflecting surfaces in curved surfaces. They are concave and convex. Whenever a light ray is passing through a concave surface, then all the rays will converge to a point, and so that we get a bright spot with a concave mirror. And whenever they are going through a convex mirror, as it is a divergent mirror, from one point light rays will diverge through different directions and we get a dull image. Now we are going to see what are the parts of a spherical mirror. See, a spherical mirror which is shaded, silvered outwards at the bulged part is called concave mirror, and the mirror which is shaded, silvered towards inward part is convex mirror. Let us see the point. P is known as pole. This is the geometric center of a spherical mirror. That means when we cut a spherical mirror from a sphere, this shape when we get like semicircular shape, its middle point, exact center point is called pole. So pole is the geometric center of a spherical mirror. Another very important point is C, so-called center of curvature. As you know, these two mirrors are spherical mirrors, in the sense they are cut from a sphere. This C is the center of that sphere, spherical ball. Here, how should we consider C? That's an important point. We have a ray called normal ray. In the sense, in mathematics language, 90 degrees falling line is called normal. Any normal ray, if it is passing through either of these mirrors, the normal ray passes through only one point, and that point is center of curvature. So pole is the center of the mirror and C is the center of the curvature, which is the center of that spherical total ball. And another important point here is F, that is called focus. Focus is the point, if you see diagrammatically, it is exactly the midpoint between F and C. So the midpoint of pole and center of curvature is called focus. And if you see in the realistically, this is the place where all the rays meet and form a bright image. Okay, if you want a bright spark, then all the rays should be converged to this focus point, right? So C and P, midpoint is F. Focus is the midpoint of pole and center of curvature. Now, some very important measurements. The distance between pole and focus point is called focal length. This is denoted with small f. And the distance between pole and center of curvature is called radius of curvature. This is denoted with capital R. So, just you observe the figure, we can understand that the distance between the points P and C, that is PC length, is twice of the distance between P and F. So we can write it as PC is equals to 2 times PF. And here we considered PC as radius of curvature. So in the place of PC we can write R, and it is taken that the distance between P and F as F, focal length. So for the equation PC is equal to 2PF, it becomes R is equal to 2F, or else F is equal to R by 2. So it is said that radius of curvature for a spherical mirror is equal to the double length of its focal length. Or else you can say in either way that focal length is half of the radius of curvature. One more ray is remaining here. The ray which is lying down the principal axis. Even we can have a ray lying above the principal axis. But this ray should pass through parallel to the principal axis. Nowhere it should meet or bend. See, one more very important point. Principal axis is the only line that meets through CFP. No other ray will go through all these points. It is the only line. Any other line, either below or above, passing parallel to principal axis, they are called paraxial rays. Paraxial rays are not principal axis. They are parallel to principal axis, either above or below the principal axis. Okay. Now it's time to see what are the rules to draw ray diagrams. See here, we are now going to draw the ray diagrams for concave mirror and convex mirror as well. What do you mean by ray diagrams? See, light energy travels in the form of rays. That all we know. What is a ray definition? According to mathematics, a ray is having only one starting point which does not have any ending point. It proceeds. Light energy is called ray because it has a starting point, source of light. We do not know where it's going to end. So it's called light ray. Now, whenever a light ray is passing through any part or any point of a spherical mirror, how it comes and how it goes, that's what we need to see now. Okay, just now we saw the different parts in the spherical mirror. Now we have to see the behavior of light rays through different points. Let us see them. The first case is whenever light ray is passing parallel to principal axis. Children, the most important point here is the direction of the light ray. If you draw a ray without any direction, it doesn't mean anything. For example, see this. The arrow mark is pointed towards the mirror, in a sense towards pole. That means this light ray is falling in this direction. It's coming in this direction towards the mirror. So this is so-called incident ray. That's why without having any direction in light is meaningless. Be careful about this point during examination when you are drawing these rays. Okay, let's come back now. Now the ray is incident. It's coming parallel to principal axis. Any ray which is incident parallel to principal axis, it will be reflected through focus. Okay? If a ray is traveling parallel to principal axis, it is reflected through focus. And see the next case, the diagram looks same, but the key thing that here need to be observed is the reversion of the arrow marks. Here, the ray is coming through focus. First one, the ray came parallel to focus and went through, came parallel to principal axis and went through focus. And here, the ray is coming through focus. Whenever any ray is incident through focus, it goes parallel to principal axis. So, incident ray is through focus and reflected ray is parallel to principal axis. This is second situation possible. Now let us see the third case. If any ray is passing through center of curvature, what type of rays come through center of curvature? 90 degrees falling rays. So according to laws of reflection, the angle of incidence is equal to angle of reflection. If a ray is falling in 90 degrees, it should be reflected in 90 degrees. So here when a ray is passing through center of curvature, it is reflected along the same point. So angle of incidence and angle of reflection will be equal. In the last case, this ray is, seeing the fourth situation, this ray is hitting pole. See, so far in the three previous cases, no ray is touching pole. Now, if a ray is incident directly on pole, at some angle, making some angle, this angle making ray is called oblique ray. Then the ray will be reflected at the same angle, but the observation is to be if the incident is from above the principal axis direction, then the reflection will be below the principal axis. If you consider a ray which is coming below the principal axis, then it will be reflected at the same angle above the principal axis. Okay? First case is when a ray is traveling parallel to the principal axis, it is reflected through focus. Second situation, if a ray is passing through focus, incident ray, then it is reflected parallel to principal axis. Third situation is if any ray is passing through center of curvature, it is reflected along the same point. And the last case, if any ray is touching a pole at one side of the principal axis, at the same angle, it is reflected but from the other side of principal axis. These are the four situations in concave mirror. Now coming to convex mirror, situations are same, but the rays are just a bit different because convex mirror is a divergent mirror, right? For example, see the first situation. Ray is coming parallel to principal axis. It is reflected because this is silvered. Now, extend this reflected ray the same angle. Then it meets through focus. Now you can calculate the distance from either side. Okay. Rules will not change because the ray behavior do not change. The only change here happening is mirror. Same. Whenever a ray is passing through focus and it will be reflected parallel to principal axis, and if a ray is passing through center of curvature, here no problem because any ray passing through center of curvature will be reflected along the same point. Now the last point here is if any ray is falling obliquely at pole, at some angle at pole, it is reflected in the same angle but from the other side of principal axis. So far it's all dealt about the four different situations where we use light rays propagation. Now I would like to mention the last point regarding these ones. Three rays are very important to draw the ray diagrams. One is traveling parallel to principal axis, and the second ray which is passing through focus, and the other ray which is passing through center of curvature. We use any two of these situations for our convenience to locate an image of an object whenever we place object at different situations. The next topic is going to be when we place object at different positions before a spherical mirror, the different positions, different sizes, different natures of the images will be obtained. Remember you, any two situations of these can be reused. So any two rays of these can be used to locate all those. That will be seen next. Now let us see how to draw image positions ray diagrams when we place an object before a concave mirror at different positions. Here we have 6 different positions, and mind you, by concave mirror we get real inverted image. Concave mirror is a convergent mirror and we get a real inverted image. And as I just mentioned earlier, we use any two of the rays that previously discussed to locate an image here. Let us see the first position. If an object is at infinity, so there is no certain point for the object, always the direction of object is directed towards above the principal axis direction. So this is the object here. And whenever an object is at infinity, the image is obtained at F. Let us see how it is obtained. See, a ray is coming parallel to the principal axis and it is passing through focus. Another ray which is taken down the principal axis, which is traveling parallel to principal axis, that is also passing through focus. Okay, we took 2 rays. These 2 rays, where they meet? They are meeting at F. So the image position is at F. What kind of image this is? Through a concave mirror we get real inverted image, and as it is concentrated at one point, this is point sized image. Okay, so whenever an object is at infinity, image is formed at F, and the nature of image is real inverted and its size is point size. That is first case. Now let us see this next case. Whenever we have an object which is beyond C, the second position now, when an object is placed beyond C, see here, if we have an object beyond C, let us take two rays. One ray which is travelling parallel to principal axis, that passes through focus. Another ray which is passing through C, it goes straight. Where these two rays are meeting? These two rays are meeting between C and F. So that is the position of image. When an object is placed beyond C, image is obtained between C and F. Same nature, real inverted, but look at the size. The size of image is less than object size. So we get diminished image. Okay. When object is beyond C, image is formed between C and F, and it is real inverted diminished image. Now coming to the third position, when the object is on C, take a ray which is travelling parallel to principal axis, going through focus, and which is going through focus, that is travelling parallel to principal axis. See that both the rays are meeting at the same point. So that's why the image is also formed on C. And with the size, object height and image height, both heights are same. So it's a real inverted image which is of same size. Next case, when the object is placed between C and F. Now the object is placed between C and F. Then same rays, one is travelling parallel to principal axis, going through focus. Another ray which is passing through focus, center of curvature. Both the rays are meeting at a point. Where is the point location two rays are meeting? They are meeting beyond C. Okay, look at the size. Now the size of the image is more than the size of the object. So this is magnified image. We can even call it as enlarged image. So when an object is placed between C and F, the image is formed beyond C, and it's a real inverted magnified image. Now coming to the fifth case. Whenever we place an object exactly on focus, then same two rays, parallel to principal axis, going to focus and through C. Look at the rays, they don't meet. That means image is formed at infinity. It's a real inverted image. We cannot even imagine the size. It's infinitely enlarged. Right? So when an object is on focus, the image is formed at infinity. It's a real inverted, infinitely enlarged image. Coming to the last case, it's a special case. Whenever the object is placed between C and F, between P and F, then whenever it is placed between P and F, then look at that rays where they are meeting. Till now we got the rays here at one side. Now look at the rays, they are going and meeting behind the mirror. When we extend these rays, we get a virtual erect image. Remember, all the virtual rays should be drawn with dotted lines. And look at the size of the image, it's magnified more than size of the object. So when we place the object between P and F, the image is formed behind the mirror and it's virtual, erect and magnified. So whenever we have 6 different positions for the object through a concave mirror, we are getting 6 different image positions. One important point, from infinity, between C and F, on C, between C and F, and then on F, then between P and F, the object is coming close to the mirror. Whenever the object is coming close to the mirror, the image is going away from the mirror. First case it was formed at F. Next, between C and F, the image formed. Then on C, then beyond C, then at infinity, then behind the mirror. So gradually as the object is moving towards the mirror, the image is coming away from the mirror. So as the object distance is decreasing, the image distance will be increasing. Always we get here real inverted image except the last case. This is the only case through concave mirror we get a virtual erect image. Remaining all the cases we get real inverted image. Okay. Next, after this there will be image positions for a convex mirror. Through a convex mirror we will have only two positions. One position is object at infinity, other position is any position other than infinity. So there we will see how the rays behave. That will be dealt in the next session. Thank you.